Inflation is a theory that deals with the evolution of the universe in its earliest stages. It suggests that in the first few moments of existence, around 10 to the minus 36 seconds after the Big Bang, the universe expanded incredibly rapidly. The expansion lasted roughly 10 to the minus 34th of a second, and during this time the universe expanded by a factor of 10 to the 26. Or to put it simply, during the brief duration of inflation, the universe expanded by a greater factor than it has in its subsequent 14 billion years of existence. This is beyond mind-boggling. Yet, believe it or not, inflation is capable of explaining many of the observed features of the universe, and solving a few cosmological headaches as well. The first of these headaches is the flatness problem. The spatial geometry of the universe is flat. This does not mean that the universe is flat two-dimensionally, as we clearly live in a three-dimensional universe. Rather, what we mean by spatially flat is that the universe has no net curvature. Einstein showed at the beginning of the 20th century that space, or more accurately space-time, but for our purposes it is enough to imagine just space, can be curved by massive objects. Space is not static, but rather a fabric that can be warped and curved. Areas with a greater concentration of mass and energy will warp the fabric more. You can conceptually imagine balls of varying density on a mattress. The balls with higher density will warp the mattress or make it sag more. Of course, the surface being warped in the mattress example is basically two-dimensional, whereas the curvature of space-time is a three-dimensional phenomenon. So, our universe definitely has local curvature at local scales because of local density variations. However, to the best of our knowledge, the universe as a whole is flat. As a result, the normal rules of geometry that you are probably familiar with, Euclidean geometry, apply. One of these rules is that the angles of a triangle add up to 180 degrees. One of the many ways that we know the universe is flat is indeed by using a method akin to drawing a large cosmological triangle and measuring its angles. Where inflation comes in is to provide an explanation as to why the universe is flat. Curvature is caused by fluctuations in density. The process of inflation, which was a process of exponential expansion, had the effect of spreading out these fluctuations in density across huge distances, effectively rendering them flat. The second main headache solved by inflation is the horizon problem. In its traditional usage, the word horizon means a line of contact between the sky and the ground. It can also be thought of as a boundary that marks off the extent of the landscape that you can see around you at any given time. You can never see over your horizon. By flying up to a higher altitude, it may be possible to increase the area that is visible in your horizon. If you look out the window of a commercial airplane, you will be able to see more of the landscape below you than if you were looking out the window of your car on the highway. In cosmology, the horizon carries basically the same definition. It is the extent of the universe that a given observer can exchange information with at a given time. This diagram here shows three radiation sources located at 1, 3, and 5 million light years from a given observer. After 1 million years have passed, the extent of the observer's horizon is 1 million light years, because only light from the radiation source that is 1 million light years away has had time to reach the observer. The size of the observer's horizon will increase with time at the speed of light. After 3 million years have passed, the radius of the horizon will be 3 million light years, because light has had 3 million years to get to the observer. And after 5 million years, the radius of the horizon will be 5 million light years. Now, of course, because the universe is expanding, these radiation sources would be moving away from the observer. This second diagram shows this effect. Now, as you can see, certain objects which were not in the observer's horizon to begin with move into the horizon because they are receding away from the observer at slower than the speed of light. However, there are distant objects that are far enough away that they are receding faster than the speed of light, and will never enter the observer's horizon, because the horizon can only expand at the speed of light. It's important to note that when we say an object is receding at faster than the speed of light, what we actually mean is that the space between you and that object is expanding at faster than the speed of light. No object can expand faster than the speed of light, but space itself can expand as fast as it pleases. The result of this is that there are certain objects that will never become visible to the observer, and the observer will simply never know that they exist. Now, remember that we said that CMB was remarkably uniform in every direction. Parts of the CMB on total opposite parts of the sky share almost exactly the same temperature. The problem is, without inflation, these two given locations, or in fact any two locations farther than 3 degrees apart on the CMB, are too far apart from each other to have ever been close enough to come into contact with each other and thus achieve the same temperature. Inflation solves this problem. Before inflation, these two locations could have been close enough to come into contact with each other and achieve the same temperature. Then, inflation blew these two locations very far apart, giving the appearance that they were never in each other's horizons.